All right, use substitution and definite integrals. Long story short, do the same thing. Okay, do the u sub, but the only thing is that when you the bounds that existed for x were x bounds, right? So when you're changing it to an integral containing u, the bounds need to change to u bounds, right? So you need to run the bounds through the substitution and change the bounds as well. Okay, so in this first example, right, I think we've had enough practice to think that u might be sine of x, the interior part, and then so du would be cosine x, which actually works out beautifully. Okay, I'm going to leave the bounds as unknown for now. I am going to change them. I am not going to write 0 in pi because that would be incorrect. But let's see. So the cosine x dx is du, so that'd be a du, and then I'd have sine of u. Okay. Now the bounds. Okay. The bounds again were for x, so I'm going to take those and run them through the substitution. So sine of 0 is 0, and sine of pi is 0. Okay, so I don't even need to go further. This is an integral that is just 0. Okay, it's a happy coincidence. Okay, so I don't need to go any further with this one. Okay, so then you're like, well, is it always going to be that clean? No, nothing can ever be always that way. So let's try it with this one. Okay, it's been a while since we worked with inverse trig functions, so figured I'd throw it in here. This should just be not divided by 0.2. That's a typo. That should just be there shouldn't be a point in there. It's just 1/2. Okay, so maybe let's just change this to a 1/2 as an upper bound. Okay, so I'm going to guess that, I remember something with square roots and arcsine. So if I do arcsine of x as u, then du, might have to look this up just as a refresher, but it'd be dx over square root of 1 minus x squared, which is actually super fortunate for us because then this just becomes integral, worry about the bounds in a minute, u du. Okay, so super easy integration, but again, definite integrals are a number, so I need to make sure to convert the bounds. Okay, run 0 through here. Okay, arcsine of 0, so what angle gives you a sine of 0? That's just 0. Okay, so arcsine of 1/2, what angle gives you a sine value of 1/2? And that ends up being pi over 6. Okay, so this, just for clarification, this would be arcsine of 1/2. Okay, and this is technically arcsine of 0. Okay, so then I'm going to go ahead and do the integration. So this would be u squared over 2, and then I don't need the plus c because I have a definite integral evaluated from 0 to pi over 6. And I actually don't need to, so now with indefinites, right, this is where we'd put x back in. Don't need that, right? This is definite. It's still a number. So then just substitute this in. I'd get pi squared over 36 divided by 2 is actually over 72. Okay, and then minus 0, which is boring. Okay, so with definite integrals, no need to substitute back. Just make sure to change the bounds instead. So kind of have a trade-off. Okay, last example here. Okay, you're looking at it like, okay, pretty sure last time we did a square root was the thing underneath, so it's probably going to be the thing underneath here again. So let's try it. Okay, so let's try u as a squared minus x squared. Okay, that'll work out fine. So if I do du, that would just be negative 2x dx, and I see the x dx in here, right? Actually, I'll underline it a different color. X dx. Okay, so let's move the 2 over, so that means here that negative 1/2 du is equal to x dx. Okay, so then I'm going to transform the integrand. Integrand is the piece inside here. So this would be, let's see, negative 1/2 could be pulled out front, and then I'd have square root of u, and then du. Okay, and then the bounds, right? So I need to run 0 through here. So if I put 0 in for x, right, that would give me a squared. And then if I put in a for x, right, that'd be a squared minus a squared, which is 0. Okay. Oh, okay, that's fine, but maybe it'd be better to flip the bounds. If I flip the bounds, I get rid of a negative, so I have 1/2 integral 0 to a squared of square root of u du, which is actually u to the 1/2 power. Okay, so I get 1/2, and then u to the 3/2 over 3/2, evaluated from 0 to a. Oh, okay, so then I think I just end up with 1/3, right, combining the constants, and then let's see. Oh, I forgot the a squared, my bad. And then this would be simplified just to a cubed. Okay, you can double check the arithmetic, but that's what I got. All right. So again, definite integrals change the bounds once you change it to u, and then just crank it out. You don't need to do any resubstitution. If you want to, you can, but you don't need to. All right. So that's the story with u substitutions and definite integrals. We'll see one more connection with u substitutions and definite integrals, because every definite integral represents an area underneath a curve. So one more example coming up that looks at areas and u substitution.